recording. Okay, so any question on this time or for homework or anything? If not, yeah, let's get started. So this time we go over more formal formulation of quantum mechanics. So once again, quantum mechanics, we have those postulates. The first one is that every isolated physical system, there is a vector space that we call Hilbert space, and the state. So all the information describing the system, how the system currently is described by a unit vector in that in the Hilbert space. And the vector space is a complex vector space with inner product. Yep. And so those things we usually write as this ket psi. Oh, sorry. I should go here. Where am I? Yeah. Yeah, so the state we usually write as a ket vector, and usually it's called k psi. And then how the system evolved described by unitary matrices. And we usually take discrete time step. So you will apply one unitary matrix to change your state to another state. Kind of like after a clock cycle, then your state, yeah, get applied a gate and a gate to next time step. And here is the Schrodinger equation for those of you who are curious. And then finally, when you want to get the quantum information get classical information out of your quantum system, then you need to apply a measurement. And the most general form of measurement are described by a set of matrices Mi. So matrices are indexed by this I. And to be a valid measurement, those matrices need to satisfy this completeness relationship. Summation over all possible I, Mi dagger, Mi equal to identity. And when you do measurement, several things will happen. So first is that your state is going to collapse into so one of the outcome out of those indexes I is going to happen, and only one of them will happen, and the measurement outcome happens with probability the amplitude of Mi apply on psi squared. And when that happens, the experimenter or the observer will know that happened. And when that happens, the system will collapse into a post-measurement state. It's basically this Mi psi and divided by some normalization. Okay, so this is the most general form of postulates of quantum mechanics, and I guess I should have said. And there is also the 3.5 that we have in the sketch version, but didn't have in the book. That is when you have multiple systems, when you have composite system that compose of multiple individual systems, then the Hilbert space of the total system is the tensor product of all the individual systems. We had that in here. Right. So if you have a multiple system, okay, so we have 2 here, but obviously these extend to 3, 4, 5. So you have 2 quantum systems, each with Hilbert space H1 and H2. Then the Hilbert space of the composite system is this H1 tensor H2, where this tensor product we defined and talked about in the previous PDF. Okay. And also what we talked about was the most general form of measurement, the set of Mi. And we briefly go through that. There are easier, simpler measurements. So in the previous chapter, we talked about computational basis measurement. look at the coefficients in the computational basis, and the probability are those amplitude squares. And then there are measurement against orthonormal basis, and measurement against some operator, Hermitian operator A. This is more physical motivated. Okay, but we'll use the language of all three kinds of measurements. So yeah, need to read the description a bit more careful, because sometimes people say measurement against some basis, sometimes they measure some operator, or sometimes they will do generalized measurement. Okay. Question? If not, then we go over example of systems. Okay. I think let's go through this once again. So the simplest possible quantum system is this, two-dimensional space, and it's 2 dimensions, so it's called a qubit, because it's a quantum bit, and the state will be described by a 2-dimensional vector, so 2 coefficients A and B. So it's A0 plus B1. We come from 0. And then there's a normalization, because you want the probability to 1, or because it's a unit vector. So A absolute value squared plus B absolute value squared need to equal to 1. And here are example. So those 2 states that are eigenvectors of sigma x is going to be important, and you should memorize them. So this plus state, which is a superposition between 0 and 1, with a plus sign between them. And the minus state is also a superposition between 0 and 1, has a minus sign between them. So if you measure those 2 in computational basis, they look like the same. It's all 50% 0, 50% 1. But those are actually distinct vectors, and actually orthonormal vectors, because if you take inner product between them, it's 0. And we're going to see that. I hope we're going to see that this means they are actually distinguishable. Okay. So plus and minus are example of states in a qubit, and obviously 0 and 1 are also example. And once again, this 0-1 basis is called computational basis. Sometimes it's also called a classical state, because, for classical bit, there are also the 0 state and the 1 state. Right? Okay. And then there are possible unitary transformation on your qubit. So for example, this x or sigma x is a unitary operator, and you can apply it on your qubit. And in terms of circuit logic, this is really equal to not gate, because when you apply on the classical state, when you apply this on 0, then you see it become 1, and you apply on 1, it becomes 0. So you flip the logic between 0 and 1. So it's really the not gate when it apply to those classical bases. But when you apply to plus and minus, weird thing happen. So yeah, as I said, plus and minus are eigenstates of x, and when you apply x on plus, it's easy to see that. So you switch 0 and 1, nothing happen. So you still got a plus state. And when you apply on minus, you switch 0 and 1, then you actually get a minus sign out of it. This minus sign is a little tricky, but let's keep it here for now. Okay. It's a global phase. Yeah. So, and this is something very interesting. We are going to see. This is going to be useful for basis of all kinds of algorithms. But for now, the plus sign is kind of global phase. You cannot really see it. Anyway, mathematically, this is correct. just as matrix algebra. And yeah, and so the state, that's unitary, and then there are examples of measurement. And well, here we try to write everything in the most general language. So in terms of the generalized measurement, and so this is kind of something dumb. We use the language of those n0 and 1 to describe the easiest measurement, which is the computational basis measurement. So how do you write computational basis measurement in terms of those generalized m's? And the corresponding n0 is going to be this projector onto 0. 0, ket 0 bra. And n1 and the other measurement operator n1 is going to be this projector onto 1. Okay? And yeah, you can easily check that they satisfy the continuity relationship because n0 dagger is still projector onto 0 and projector 0 times projector 0 is still projector 0. And also n1 dagger equal to n1. And n1 squared, once again, is just n1 is 1, 1. And projector onto 0 plus projector onto 1 is just projector onto everything, so that's identity. Okay? Yeah, so that's a lot of notation to describe the computational basis measurement. And then what happens when you apply this computational basis measurement on 0? Well, now you know this is the computational basis measurement. You can kind of just read from 0 being 1, 0, right? So 0 is this. So you kind of know it should be 0 with 100% and 1 with 0%. But let's go through that. So you project 0 onto this 0 space, and you see you get this 0 vector out. Yeah, it's unit norm 1. And you apply this 1 projector onto 0. Then because this 1 bra and the 0 ket has 0 inner product, so this is a 0 vector. Okay, so this is a little confusing. But this is a vector of length 0. Okay, so that's different from this ket 0. Okay. It's a vector with both coefficients being 0. And anyway, this vector has length 0, so this happens with 0 probability. And this vector has length 1, so this has happened with 100% probability. So 100% probability, you get 0, and the state collapses into 0. Okay? And then let's do a less trivial measurement here. So you do this computational basis measurement on your plus state. So this is 1 over square root 2, 1 over square root 2. And what happened? Well, you do projector. Projector on 0, pick out the 0 component. So you get the subnormalized post-measurement state is this 1 over square root 2, 0. And similarly, when you do this n1, then it's a projection onto 1, so you will get 1 over square root 1. And then you have 1 over square root 2, and then the amplitude square of this thing is 1 over square root 2 square equal to 1 over 2. So probability of this happen is 1 over 2. And similarly, probability of this happen is 1 over 2. And obviously, when you renormalize this state, it becomes 0. Renormalize state, it becomes 1. So the probability of this 0 measurement outcome happen is 50%. And when this happens, your state get collapsed into 0. And and similarly, for 1, the probability is also 50%. And when this measurement outcome happen, your state collapses into 1. Okay? And, well, it's not here, but, okay, quick question, quick quiz, I guess. So what happens when you do this M0 and 1 measurement minus state? Anyone want to answer? What's the probability and what's the post-measurement state? Well, okay. Well, when you do those measurements minus state, it actually looks very like plus state. So the only difference is now, so n0 minus is still 1 over square root 0, and n1 minus is minus 1 over square root 1, and yeah, so nothing much change. So minus 1 over square root 2 amplitude square is still 1 over 2. So probability are the same, but the post-measurement state becomes 0 and negative sign times 1. Okay. So that's measurement. And once again, this is something not very rigorous, but kind of intuition I hope you are building. That is, the amplitude absolute value squared is something about probability, right? So this is something keep happening like at the very beginning. We have that. We have that when you do this computational basis measurement, the probability some outcome happen is this m2 absolute value squared, and yeah, and you see that in this generalized measurement, this thing also keep happening. You can kind of think the post-measurement state as this mi psi, and the probability of it happen is this amplitude squared. Okay, so amplitude absolute value square is kind of like probability, and you want our vectors to have unit length because we want this total probability equal to 1, and we want our transformation to be unitary because that will preserve the length of the vector and thus preserve the total probability. Yeah, and as I say, when you do measurement, the probability of getting the subnormal state mi psi is absolute value squared. Okay, so that's our intuition. Nice to remember. And another disclaimer is that we are computer science course, so the time and space are discrete and finite. Well, finite is a little weird, but anyway, yeah, we deal with finite dimensional space, and times are discrete. We think in clock cycles, so you apply one gate and another gate, etc. Okay. And that's computer science. Then let's go back to a bit of physics. So, well, this is some digression of computer computation, but it might be interesting to think about because you see this problem in popular science work a lot. So this is a measurement problem. This is a thing that people confuse in the fundamentals of quantum mechanics most. That is, remember we described our how we interact with quantum system like this. So there is a quantum world. There is some weird quantum system with ket psi, and it will evolve with unitary, etc. And there is a very classical part. That's you and your laptop, etc. So everything classical, large scale. And they will do, there is a line here, and they will do measurement to get information out. Okay? And by your physicist, then you believe everything in the universe should be governed by the same kind of law of physics. And that makes this line really weird. So why is there this line here separating classical world and quantum world? How do you draw this line? Shouldn't, if quantum mechanics is true, then everything in the world should be quantum mechanics. And this line is really weird. So in particular, there being classical observer is really weird if you really believe in quantum mechanics and think everything should be quantum mechanics. And yeah, like I said, when we write the postulate in quantum mechanics, we say every isolated physical system is described by this Hilbert space and the ket. and your observer is kind of like isolated physical system too. So shouldn't this also be declared by quantum mechanics? Then why does this thing look classical? Why don't you have superposition? So that's one question, and the bigger question is, how do you draw this line here? How do you separate the classical and quantum? And so measurement problem happen when you don't want to draw this line. When you try to describe everything as a quantum system and think yourself as a quantum system, then you need all kind of interpretation to make it work. Like the many word hypothesis, interpretation, etc. But anyway, we took kind of an engineer approach, and just think that in practice it's pretty clear where you can draw this line. There is some carefully designed system, a very small system, that's your quantum computer. They will behave quantumly, and everything else is classical. And it works in practice, and we don't think about the measurement problem so much. Okay. So, question? Okay. Then let's get back to more non-philosophical discussion of quantum mechanics. And so now we are going to keep talking about result and the property of this weird quantum measurement. So first thing about this quantum measurement is that there is this, or this is more like a property of quantum state. So it's that there are some states that are informationally, theoretically, or physically indistinguishable. Some quantum states are indistinguishable. That means that, well, before talking about indistinguishable, let's talk about what are distinguishable. So orthogonal states are perfectly distinguishable. They are just like classical state. So what do we mean by distinguishable is that, well, there are two states. So for example, this classical state 0 and 1. And there is a measurement. So for example, the computational basis measurement is projected on 0 and projected on 1. This can perfectly distinguish 0 and 1. That means if you input an unknown state into this measurement 0 and 1, and if you input 0, then you will get outcome 0 with 100% probability, and the outcome 1 with 0% probability. And if your input state is 1, then you will get outcome 1 with 100% probability, and the 0 with 0% probability. Okay, so this is like in a classical world, you do a measurement, and assuming your measurement apparatus and your experimental design is very good, you have very high precision, then you can get a measurement outcome perfectly. Right? There is nothing stop you to design a very good measurement that will give you perfect distinguishability between a bit being 0 or a bit being 1. And now a weirder quantum state. So now we have those two superposition states, plus and minus. Okay. So those two things, now if you do computational basis measurement, then that's not really distinguishable because they both give you 50% probability. But as I said, those two states are orthogonal, and they are also distinguishable. You just need to measure in different bases. So you measure in this plus minus basis. Okay? And it's easy to check that this is a valid measurement because you sum those two together, it becomes identity. And this also perfectly distinguishes the plus state and minus state. because you put a plus state into this measurement, 100% probability you get a plus out, and you get a minus state into this measurement, and 100% probability you get minus out. Okay. So this is what I mean by perfectly distinguishable. So you have some kind of measurement, or let's say it's a two-state, so you have a two-outcome measurement, and one state will always give you one of the measurement, and the other state will always give you the other measurement, perfectly distinguishable. But now, if your two input state are not orthogonal, then you can prove that they cannot be perfectly distinguished. And this is not a result from your experiment has some error or anything. This is just physically or information theoretically. Those two states are just not perfectly distinguishable. So for example, if you try to distinguish whether your input state is 0 or input state is plus, so assume there is some referee that's going to, or some tester. So if we do a measurement in 0, 1 basis, so this measurement project down to 0, project down to 1, then when the input state is 0, well, that's very nice. You 100% probability you get 0. But if the input state is plus, then as we said, the probability you see outcome is 50% 0, 50% 1. And now consider you see one of the outcome, you see here 0, 1. Okay, so you see 1, then that's pretty nice, because it's 0% here, so if you see 1, the input state can only be plus. But if you see 0, then maybe it actually start with 0, or maybe the input state is plus, and you just get this 50% possibility here. Okay. So if you see an outcome is 0, you really don't know whether input state is 0 or 1. And similarly, if you say I want to optimize against this plus, so we measure in these plus minus spaces. And well, you can easily calculate that if you measure 0 in plus minus spaces, then the outcome probability are 50% and 50%. And if the input is plus, then obviously the outcome is 100% being plus. And here we see that if the outcome is plus, then it can come from input being plus or input being 0, and the usual is 50%. Okay. So this does not perfectly distinguish 0 and plus either. And if you didn't confuse, so there's something that you may confuse, that you say the probability distribution here are different, right? So it's 100%, 0%, and it's 50-50. And maybe you just repeat the measurement many times, and there will be, you can see a difference between two distributions. But here you see that the state collapse being important. So we are assuming we do this test in one-shot setting. So the tester or experimenter only give you one copy of either 0 or plus. And if you are only given one copy, then you really cannot do any amplify here, because after the measurement, the state gets collapsed. So for example, your state is 0 here, and you get a plus state outcome. Then the state really becomes a plus state. Then you do this plus minus measurement again. You always keep getting this plus outcome. Okay. So the 50% only happen when you do the measurement first time. Okay. So this is why the state collapse being really important. It guarantees this information theoretical indistinguishability. And here we give a more formal proof of what we said. So we can prove that if your state psi 1 and psi 2 has inner product non-zero, so they are not orthogonal, then you cannot have some measurement M1 and M2 perfectly distinguish them. So here we have the condition of perfectly distinguished right out formulas. So if your input state is psi1, then its projector, then n1 apply it must have known 1, and the probability of measuring n2 is 0, and also when your input state is psi2, then from this equation we can see that, well, once again, this is the norm of n2 psi1 squared, and if something squared is 0, then it's 0. So norm of n2 psi1 is 0. That means, well, if the vector has non-zero, that means the vector is a 0 vector. Okay, and so that's something to keep. And then we use our non-orthogonal relationship here. So psi1 and psi2 has some overlap. That means that you can we can write psi2 in a basis that expand. Okay, we didn't say the dimension, but anyway, we can expand psi1 into a basis, and we can write psi2 as some component of psi1 plus another component as orthogonal to psi1. Okay, so this notation here just means something as orthogonal to psi1. And okay, so what's important here? What's important here is that this alpha is not 0. Okay, so this alpha is the inner product between psi2 and psi1, and it's not 0. And okay, so actually write that here. So psi1 and this psi1 perpendicular is 0. 0. Okay, and so alpha is not 0, and well, those are two orthogonal components, so they're non-square. So psi2 is normalized, so alpha non-square, beta non-square should equal to 1, and that means that the beta non-square should be less than 1. Okay. And then we just do substitute. So we start with this equation here, this equation, and so this equation is basically n2 psi2 non-square. So let's think about n2 psi2. So we think n2 psi2 and replace it with this expansion of psi2. So write psi2 as alpha psi1 plus beta psi1 perpendicular. Then that's, well, then you do the linear thing. So that's alpha n2 psi1 plus beta n2 psi1 perpendicular. But here we have n2 psi1 equal to 0. So this term becomes 0. So that's just beta n2 psi1 perp. Now we think about non-square of this equation. Well, then you non-square both sides. So this becomes your psi2 m2 dagger n2 psi2. And this side becomes our beta non-square and psi1 perp m2 dagger n2 psi1 perp. Okay. And now this thing, you can insert n1 dagger n1 in the middle. So you are basically inserting a term that's n1 psi1 perp square here. And obviously inserting this term is positive, and you are adding something, so that's less than. So yeah, so increasing, and you write less equal to here. And finally use the normalization, the completeness of your measurement. So n1 dagger n1 plus n2 dagger n2 should equal identity. And yeah, so that's n1 perp and 1 perp inner product, and that's 1. So this thing should equal to beta square. And from here, I should write. So here I actually write this wrong, right? So here I should write strictly less than 1. Okay, it's important to have it strictly less here because that's what we want to do contradiction. Okay, so after all the derivation, we see that this term is strictly less than 1, but here we have equal to 1. So that's a contradiction, and that means that something here that should not happen, and this is impossible. Okay, so that's quite a bit of derivation here. But the line is, if your two states are not orthogonal, then it's impossible to have a measurement that perfectly distinguishes them. Okay. And okay, here is something we can skip. So this is kind of old file. Oh, I guess we can talk about this. And term that people will use is this projective measurement. And projective measurement just means that all the MI are some projector. And projector we usually use capital case P. So it's on PI. And just as a reminder, I guess maybe we should say this in the first chapter. But projectors are those matrices that have P squared equal to P. So it's square equal to itself. And yeah, from here you can easily derive that projector has eigenvalue 0 or 1. Because 0 and 1 are only an equation have in x squared equal to x. Okay? The only solution for x squared equal to xi, and as I said, the eigenvalue are going to 0 and 1, and it's pretty easy to derive that pi dagger also equal to pi. Okay, so it's going to be Hermitian. And the completeness relationship, so your sum I and my dagger and mi equal to identity just becomes sum I pi and equal in identity. So those projectors should partition your space nicely. Okay. And yeah, and from there you see that all those projectors need to be orthogonal in this sense. So for different ij, pi times pj should equal to 0. So they should have no overlap, otherwise this won't be true. Okay. And the probability of some outcome happening is this inner product of psi and pi. So, and the post-measurement state is basically this pi psi. So your state size projection onto whatever the space this projector spans. And obviously you have this normalization. Okay. And one thing we kind of talk about is that if your measurement is a projective measurement, then then your measurement will fix the result. So if your post-measurement state already project onto some pi, then you project with pi again, and the state don't really change. Okay. So once you get measurement, I should say, okay. So once you do a projective measurement with the set of different pi, okay. So the measurement is a set of pi, and you get some result I, and you do the same set of measurement again, then you are going to keep getting a result pj equals 0, so the result is probability 0. Okay. And so some general notation. So when people say about measurement, they usually mean projective measurement. And this set of mi thing are usually called generalized measurement. Okay. So this is just some notation. And just as where? Yeah. So remember we talked about measurement has those kind of formulations. So computational basis against the basis and against the Hermitian operator and the generalized measurement. So this is generalized measurement, and all those three are actually all projective measurement. Think about it. So obviously those are projectors onto the basis element, and this will be projector onto the eigenspace of your Hermitian operator. Okay, so those are projective measurements. And okay, let's go back. Where are we? I think about 16. Oh, here. Yeah. And then here is the explanation of measurement of is the explanation of a measurement of operator being projective measurement once again, because you can write your Hermitian matrix as sum of projectors times your eigenvalues, etc. And it's given that the expectation value of your operator is this inner product of psi with your operator. Okay. And we have time until 3:10, right? So that's weird. Let's see, we don't really have time to run through all this. Okay, then maybe let's go through this slower. Yeah, so yeah, this is kind of a review of how you interpret okay. So we kind of build this measurement of operator as associating a real number mi to each outcome I, and as we say, we can write every Hermitian matrix as the sum of its eigenvalue and projector onto some subspace. For example, this three-dimensional Hermitian matrix 1, 2, 2 can be written as -1 and projector onto this one space times 2 and plus 2 times a projector onto this two-dimensional subspace here. Yeah. And yeah, as a reminder, matrix N is a Hermitian if and only if it's diagonalizable and all the eigenvalues are real. So this decomposition is really a if only if thing. So if you write a matrix in this way, it's going to be Hermitian, and also every Hermitian matrix can be written this way. Okay. Yeah. So as we said, every Hermitian matrix can be written this way. And so every Hermitian matrix can be viewed or is associated with some projective measurement, because its eigenspace you have so you write down a Hermitian matrix, they're going to be projectors onto its eigenspaces. Okay. So it's so you have this measurement or this projective measurement associated with your Hermitian matrix, and you can also this and the corresponding eigenvalues are replacing the indices to those I. So the I are just some indexes are counting, but now you replace those counting number I with your eigenvalue of your matrices, and now they have physical meaning. So the eigenvalues we think of as the measurement outcome of some physical quantity. It's some real number. Okay? And yeah, and you think these are you measure some physical quantity. So for example, it might be position of your particle, might be the momentum of your particle, or the lambda might be some electric field strength or number of photons. And those those examples are a little weird because they are continuous variables, but yeah, let's pretend that they are discrete for now. Number of photons is cool. Yeah, but anyway, so you want to measure some physical quantity, then it has some associated Hermitian matrix M, and then the Hermitian matrix has those eigenvalues and projectors, and you do a projective measurement on your space. You do this projective measurement on your state, and whatever outcome got projected, then the eigenvalue is the physical quantity you measured. Okay. So I guess an example is this, let's see where, sigma x. Okay. So the sigma x is something where it's a Hermitian matrix and then something can measure, and we're going to see that it corresponds to your spin in plus x direction or minus x direction. Okay. So so this thing has eigenvector plus and minus, and eigenvalue plus 1 and minus 1. And this actually corresponds to the spin of your electron, say. And when you get measurement outcome plus 1, means your electron is spinning in plus x direction with 1 unit. And you get a measurement outcome minus 1, means your electron is spinning in the minus x direction with 1 unit. Well, 1 unit is actually, there are actually more units here because it's physics, and you need to have a unit for magnetic moments, but yeah, you get the idea. There's some standard unit. So that's a physical measurement, and I got 1 minute. Let's see. Yeah. So yeah, when you do measurement on some observable, that can be written as the summation MIPI, and you get the ice outcome. Then the physical quantity you measure has value Mi, and the state collapses into PISI. And we have 1 minute, okay. And also then the expectation value of you measuring some observable A with some state Ksi, then is this. So this is really a derivation here. Okay. So we derive that this is true. Okay. So you should really go the other way. So this thing equal to sum over all possible outcome times the probability, and okay, we are over time, and you can go through this the other direction and see it's true. Okay, any questions?